everyone. Greetings and welcome to CEC-UGC lecture series. You are watching the 14th lecture in the series Mathematical Methods for Economics. In the previous lecture, we started talking about power functions and we covered a little bit of ground on the domain of power functions and also the graphs of power functions. In today's lecture, continuing from the previous one, we will finish up our discussion on power functions because we still have some specific cases to examine in terms of changing the assumption on the exponent. But before that, let me do a quick recap of some of the key points that I covered in the previous lecture because we're going to build up on those key points. First of all, let us be clear about the difference between power functions and the category of functions that we will be covering next, namely exponential functions. To understand the difference between power functions and exponential functions, consider the expression that I'm showing you here, a to the power r, where a here is the base and r here is referred to as the exponent, which is basically the power to which the base a is raised, right? Now, suppose I have a function of the form x to the power r, and now let's compare this with a to the power r. If we have a function f of x equal to x to the power r, then we see here that the independent variable x, it appears in the base, it appears as a base, whereas it is the exponent which is a constant. So it is the base that varies because the independent variable appears as a base, it is a base that varies, but the power is a constant r, right? So this is the case of a power function. This is an example, this is the formula for a power function. Now, if we, however, specify a function g of x equal to a to the power x, here you notice that the independent variable x now appears as the exponent. It's not the base anymore like we had in a power function. It appears as the exponent. So here it is the power that varies, whereas the base remains a constant. In this case, it is a. This is then the specification of what we call exponential functions. This is a distinction which is very crucial, so all of you please make a note of it. Now, coming to the discussion on power functions, the general form of a power function is f of x equal to k times x to the power r, where k is a non-zero constant. Here we take k as a non-zero constant because if we put k equal to 0, what will happen? This function will just degenerate to a constant which is 0 here, and that doesn't make for anything interesting, at least in the context of what we are discussing today. So we will assume that k is some non-zero constant. Also, without getting into the details of x and r, let me straight away point your focus to this expression x to the power r. This expression x to the power r is going to be the focus of our attention in today's lecture. K here is just a multiplicative constant, so we'll just go ahead and assume that k is equal to 1 for the rest of the lecture because that just makes the analysis more tractable. Right, so now our function, after assuming that k is equal to 1, which is something we'll do for the rest of the lecture, our function now takes a form x to the power r. And we'll now see, we'll build up specific cases for the exponent that depending on specific sets that the exponent r belongs to, will be placing different restrictions on x. So this leads us to the discussion on the domain of power functions. So our discussion in particular will look at what are the possible values that x can take based on different sets that r, the exponent, belongs to. And we'll also look at graphs of power functions in a bit. So the first case here is, let us allow r, the exponent, to be any real number. Now, if r is any real number, then a power function is defined for all real numbers provided, for all real numbers r, provided that x is strictly greater than 0. Here we have to have the restriction that x is positive, because there are many values of this exponent r. If we take certain values, then what will happen is that this expression x to the power r will not be defined for certain values of r. And let's see how that works. So if for example we take certain values of r where x we take as negative or 0, then we'll just see, as I'll illustrate, that x to the power r will not be defined. Let us take this case. Suppose r is equal to half. Then what do we get? Our function becomes f of x equal to the square root of x, right? And we all know that when we take the square root of a number, the number under the square root sign has to be non-negative. If it is negative, then the square root of a negative number is not defined over the real line. Negative numbers have imaginary square roots, and that is something which is beyond the scope of this particular course. So we take x greater than or equal to 0 when r is equal to half, right? We'll have to have this restriction. We can't take x negative. Similarly, when r is equal to 0, what happens? When r is equal to 0, our function becomes x to the power 0, but here note that we can't take x equal to 0. What will happen if we take x equal to 0? We'll get 0 to the power 0, which is not defined. So we take x to be any number other than 0, and then we get x to the power 0 is equal to 1. Right? And for that matter, even if we take the exponent, for example, as a negative integer, so here n is a natural number, so that r becomes a negative integer, in which case our expression x to the power r boils down to x to the power minus n, which is 1 divided by x to the power n. Here also we can't take, things will not make sense if we put x equal to 0, because division by 0 is not defined. So clearly there are many values of r for which the expression x to the power r is not defined if we take negative or 0 values for x, right? And that is why we have this restriction that if r is any real number, if the exponent is any real number, then we have to have x be positive. Okay. Now you might argue that when we draw graphs, let's say r is equal to 2, we draw a graph of x squared, which is a quadratic function, or if we take r equal to 3, in these graphs we take x to be any real number. So remember here that that is also possible. We can relax the restrictions on x, so we can take x to be a larger set and not just confine ourselves to x being positive. We can take a larger set for x, but then we'll have to change our assumption. So here, because the assumption is r is any real number, that assumption will have to be changed so as to allow for a larger set in the domain. Okay, so those cases we'll come to in a bit, but let us first just revisit the graphs of this particular, the graphs of functions for this particular case that we've just built up. Right. This is a case where r is any real number, f of x is equal to x to the power r, and we're taking x to be positive. So because we're taking x to be positive, the graph of this function, whichever value of r we take, the graph will always lie in the first quadrant. And remember, because we're not even allowing x to be 0, so the origin will not be included. I'll just show you the graphs. And the shape of the graph will depend crucially on the value of the exponent r. So to get a sense of things, let's take different possibilities. Here for this equation, y equal to x to the power r, I've drawn the graphs for different possible intervals within which r can lie. So let's suppose r lies between 0 and 1, then this is a kind of graph you will get, like the one in yellow here. It is a graph which has the same general shape as that of the square root of x. So for example, just to get a sense of things, take r equal to half. Half lies between 0 and 1, and this is the kind of graph you'll get for y equal to square root of x, right? And note here, before anything else, that all these three graphs that I've drawn here in this panel are all drawn in the first quadrant, right? And the origin is not included. Right, in any case, the last one, in any case, the graph is right here. Okay, so let's take this second graph here in the middle. This is the graph which we would get. It's the kind of graph which we would get if R is strictly greater than 1. And again, to get a visual sense of things, you can take perhaps a number like 2. So if R is 2, then our graph will look like the graph of y equal to x squared. But here again, we will take only that part of the parabola that lies in the first quadrant. So this is the graph that corresponds to what we'll get for R greater than 1. For R negative, here we're going to get a graph that looks like, for example, suppose we were to take R equal to, let's say, -1. So then we would get the equation y equal to 1 by x, which is the graph of hyperbola, rectangular hyperbola, which actually, if we allowed if we didn't have this restriction that x is positive, that graph would have been in the first and the third quadrants. But here again, we have this restriction that x is positive. So here, this is a kind of shape that you'll get for R negative. Similarly, you could also have R equal to, let's say, -2, in which case the original graph, had you not had this restriction of x positive, would have been in the first and the second quadrants for 1 by x squared. But in this case, again, we're just looking at the first quadrant, so this is the general shape, right? So this is as far as the first case goes. And also you'll notice I haven't been able to specifically mark the point here, but you can just do this calculation, because if I put x equal to 1, you can see that 1 to the power r will be 1, and therefore we have that the graph of the function x to the power r passes through 1, 1, the point 1, 1 in the xy plane. So all of these graphs will pass through the point 1, 1 in the xy plane. And here you have a whole family of functions which I've shown for R positive. I haven't taken R negative here. And by the way, I didn't show you the extreme cases, so you could also have R equal to 1, in which case you'll get the straight line here. Do you see here? So if R is equal to 1, that will be the graph will be the graph of the equation y equal to x to the power 1, which is nothing but y equal to x. That is a straight line from the origin with a slope of 1, right? Again, the origin is not included in any of the graphs. Please note that. Then I've also shown you graphs of y equal to x squared, x cubed, and for values of r between 0 and 1. So I've just replicated the first two graphs in the panel that I just showed you, and I've taken some more exponents, but this is a whole family of functions that you get. And note here that all of these graphs pass through the point 1, 1 in the xy plane. Okay, moving on, let's build up the second case now. Let us now take r to be any positive integer, right? So in the first first part of the discussion that we had, we allowed r to be any real number, and now we take r to be a positive integer in the expression x to the power r. So r is equal to n, where n is any positive integer 1, 2, 3, 4, 5 and so on. And here you, if you see here, you don't require any restrictions on x. Whenever r is a positive integer, you can just go ahead and take any x on the real line to be part of the domain. So the domain is not restricted in any way. X can be any real number, and that is exactly what you are familiar with. So for example, if you have n equal to 1 here, and by the way, here we'll also distinguish between positive odd integer and positive even integer, because you'll see in a bit that there is a difference in the kinds of graphs and the shapes of the graphs that you get for the two cases. So here n is odd, right? So your graph becomes a graph of y equal to x, r is equal to n here, note, and that is nothing but a straight line that passes through the origin, right? 1, 1 is going to be a point on this graph. This is a straight line with a slope of 1. Okay, the next case is where within r being a positive integer, we take n as an even integer, so n is equal to 2, let's say. I'm just looking at some individual cases right now, and then we'll talk of the family of graphs that you get for n even or n odd within the case of positive integers. So if n is equal to 2, then you get the graph of y equal to x squared, and here also you can see that there's no restriction on x. It's not needed when the power is positive integer. The graph again passes through the point 1, 1. Again, a note here that this graph will also pass through the origin, right? So whether n is even or odd, the graph will pass through the origin. In fact, here you have the parabola which is just sitting on the origin. Also, there is another point that you can note, because we have covered symmetry in one of my earlier lectures. So if you look at the symmetry of graphs, that is something you can apply here, and you can see here that this is a graph which is symmetric about the y-axis. Do you see here? What do we mean by symmetry about the y-axis? It means that if I were to take any point x comma y on this curve, then the point minus x comma y, which lies on the other side of the y-axis, that will also be a part of the curve. So that is to say, f of minus x is equal to f of x. So if we take specific numbers here, since 1, 1 belongs to the curve, then we can say that the curve will also pass through minus 1, 1, right? This is a case of an even function, and here you have symmetry about the y-axis. So as I just said, the graphs pass through the origin for all values of the parameter n, and also the graph passes through 1, 1 in the xy plane. This is true for all graphs. Whether they pass through because for the previous graph we said minus 1, 1, that depends on n being even or odd. So, but the generic features are that the graph will pass through the origin, and also the graph of all these functions will pass through 1, 1 in the xy plane. So here what I have done is I have also taken y equal to x to the power 4 into account, and if you look at these two graphs, both these graphs, they are symmetric about the y-axis, but note here that here this graph in pink, the graph of y equal to x to the power 4, this looks like a little flat here, but I'll make things more specific. Actually, it's a height which has just gone down throughout between the numbers minus 1 and 1, and then it's just quite steep, but this is once I draw these two graphs together, you'll get a sense of things. But you can see that both these graphs, they pass through 1, 1 as well as minus 1, 1, because you have symmetry about the y-axis. And basically the graph of y equal to x to the power 4 will have the same general shape as y equal to x squared. Okay, so now we are taking r to be a positive odd integer. So if y were, let's say, if the power is 3 here, so you get the graph of y equal to x cubed, which looks like this. We've done cubic functions, so you should be familiar with this graph. And I've also shown you the graph of y equal to x to the power 5 here. So here what do you notice? First of all, both these graphs again pass through 1, 1, but here you have symmetry about the origin. So when you have a graph for r being a positive odd integer, the exponent is a positive odd integer, then you have symmetry about the origin, which is to say that if the point x comma y belongs to the graph, then the point minus x comma minus y also belongs to the graph. That is, f of minus x is equal to minus f of x, which is a case of an odd function. So here what do you see? If the point 1 comma 1 lies on the graph, then you see here that the point minus 1 comma minus 1 also lies on the graph, and this is symmetry about the origin. Similarly, when you take y equal to x to the power 5, the same features are retained, and y equal to x to the power 5 will have the same general shape as x cubed. Right, so this is just a summary of all the features I've just talked about. Graph of y equal to x to the power n when n is even has the same general shape as that of y equal to x squared. The function is even when n is even. It's an even function, which is to say that it is symmetric about the y-axis, and that is to say that in addition to passing through the point 1 comma 1, it will also pass through the point minus 1 comma 1, right? And in contrast, when n is odd, the graph of y equal to x to the power n, it will have the same general shape as that of y equal to x cubed, and this is the case where the function f of x equal to x to the power n is said to be an odd function. This is symmetric about the origin, and that in turn implies that if the point 1 comma 1 lies on the graph, which is the case here, then the point minus 1 comma minus 1 will also lie on the graph. So I hope these features are clear. Right, now as I was talking to you, that part between minus 1 to 1, that interval, in that interval the graph looked quite flat, and that is basically what is happening is that as n increases, the height of the graph becomes smaller over the interval minus 1 to 1, except at x equal to 0, of course, because at x equal to 0, whether you have x squared or x to the power 4, in all these cases you will get a 0 value. But if you take the intervals x greater than 1 or x less than minus 1, there the heights will be larger. And to get a sense of things, just look at the numbers here. So for example, if you have the function x to the power n, where n is a positive integer, and let's suppose x is equal to 0.1, right? So 0.1 lies between minus 1 and 1, right? And you can see here that as n increases, right, x to the power n will fall. Okay, so for example, I've put in a particular calculation also here. So if I take 0.1 squared, that is going to be equal to 0.01. But if I take 0.1 to the power 4, that is going to be a lower number, because if we take any number between minus 1 and 1, the higher the powers become, the smaller that number becomes in absolute value. So what happens is, and this is also true for any number between 0 and between minus 1 and 0. So this is exactly what happens. So suppose we have x to the power n, where n is even. This is the family of curves that you will get. Here I've shown you the graph of y equal to x squared, x to the power 4, x to the power 6, right? And what do you notice here? So the graph in blue is the graph of y equal to x squared, right? Now if I look at the graph of y equal to x to the power 4, that lies everywhere below the blue curve in the interval minus 1 to 1. Right, because this is what I was just illustrating. If x is, let's say, 0.1 here, then 0.1 squared would be a higher number as compared to 0.1 to the power 4. So everywhere in the interval minus 1 to 1, the graph of y equal to x to the power 4 will lie below the blue curve, which is a graph of y equal to x squared. However, if I take any number, any x beyond to the right of 1, greater than 1, or less than minus 1, what do you see? Suddenly the height becomes more than what you have for the blue curve, right? So for example, if x were, let's say, 2, then x squared would be 4, but x to the power 4 would be 2 to the power 4, which is 32. 16, sorry, 2 squared is 4, 4 twos are 8, 8 twos are 16, right? So that will be 16. So there the height becomes more than what you have for the blue curve. So that is what you have to note in terms of what the heights are. Similarly, the same thing is happening here for the odd case, n being odd. So here again you'll notice that this is y equal to x is anyway separate. So y equal to x cubed is this graph in pink, right? And you can see that between -1 and 1, right, the pink graph lies above. In the negative part, because you're looking at the absolute values, so it will lie above only. In terms of absolute values, the number will be higher. But here you can see in the positive quadrant here, in the first quadrant, it lies above. Then the graph of y equal to x to the power 5 here lies below. But beyond 1 or to the left of -1, they will suddenly gain height, right? And all these graphs, they cross. What do you notice here? These all these graphs, they pass through 1, 1 and -1, -1. Here you have symmetry about the origin. In the previous case, the graphs, they all pass through 1, 1 and -1, -1. So this is the discussion for the case where r is a positive integer. In the next session, we will talk about the case where we assume that r is a negative integer, and we'll see what ramifications that has for the domain and the graphs. Thank you.